Xiao-Gang Wen will be the next speaker who will talk about phases and phase transition from categorical symmetry.
I like to thank the organizer for organizing this meeting, in particular, Arthur. And nowadays, this joint meeting for mathematics, physics, and quantum information, almost like a family reunion. I can enjoy it a lot. And so today I'm going to discuss some theory for phase and phase transition, but from some kind of categorical point of view. We know that there's a three kinds of quantum state of matter. There's a gapped phase of matter, which is almost trivial because there's nothing at the low energy below the energy gap. And there's also a gapless state of matter with a few gapless excitation. And also there's a gapless state of matter with a lot of gapless excitation, and which is messy, the last one. And even for the gapped state, which is supposed to be trivial, it turns out to be quite rich. So we have so-called gap liquid state and a gap non-liquid states. And even without the symmetry, you know, for a long time we thought if there's no symmetry and there's no spontaneous symmetry breaking, all the gap state of matter only have one phase. But now we realize that even without symmetry and symmetry breaking, there could be many different phases for this gap liquid states. And this kind of thing is called topological order, or the pattern for long range entanglement. You know, after 30 years, we finally realize that maybe this is this kind of gap liquid states is related to the braid fusion higher category. And so that's maybe the proper mathematical language for this topological order, just like a group theory is a proper mathematical language for symmetry. Okay. However, the gapless state of matter is much harder. And for a long time, you know, we don't know how to develop a general theory for that. But this is related to the very hard problem of this how to define quantum field theory rigorously. And Arthur have made a great contribution in this direction. And so nowadays we may have some kind of a new story to tell in this direction. How to have a general theory for gapless state of matter, how to have a general understanding for quantum field theory. And one way to proceed is to consider symmetry. So it's well known that when you have a quantum system at a low energy, there's an emergent symmetry. And now we realize that we could have emergent ordinary symmetry, or emergent anomalous symmetry, or emergent higher symmetry, anomalous higher symmetry, algebraic higher symmetry, anomalous algebraic higher symmetry, and etc. This non-invertible symmetry, all these kind of symmetry. So it's very rich. Okay. And but so when we have so many different kind of symmetry, it's kind of inconvenient. So here I like to argue that all this kind of symmetry actually correspond to naturally an algebra of local symmetric operators. It's like the last talk about this algebra. And it turns out that the equivalence class of this algebra have a hidden topological skeleton, which is a braid fusion category, which corresponds to topological order in one higher dimension. So there's a unified way to look at all those symmetry as a topological order in one higher dimension, or as a braid fusion higher category. And then how this symmetry may help us understand the gapless state of matter. And here we will take a very optimistic point of view. We just boldly assume or conjecture that each gapless state may have its own distinct characteristic emerging symmetry. And so I don't know whether it's true or not, but even it's not true, we can assume it's true and just proceed. And later we find some, if we find some problem, we try to fix it. And then from last slide, so if you believe this, then one can using this generalized symmetry as a starting point to develop a general theory for gapless states. And this generalized symmetry actually is a categorical symmetry as unified description. So we can using categorical symmetry as a starting point to describe this general theory for gapless states. And in particular, so to be more concrete, so we have this following story. That is a gapless quantum state with a certain symmetry, with certain emergent categorical symmetry, correspond to the boundary of a topological order in one higher dimension. So those gapless quantum states correspond to boundary, and the symmetry corresponds to topological order in one higher dimension. So this is this may be a kind of a general way to look at the gapless state of matter. So to be more concrete, so let's just see some example. The Y symmetry and the topological order in one higher dimension is related. In which way they are related? So we know. Let's consider a very simple example, like in 1+1 dimension. So this one is a space dimension, another one is a time dimension. So with a Z2 symmetry, and then this 1+1 dimensional Z2 symmetry is associated with a topological order, Z2 topological order in one higher dimension. 2+1 dimensional Tor code model, or you can view this is a Z2 quantum double, or it's some kind of modular tensor category theory of this Z2 quantum double. So there's all kind of a name for the same thing. And then we know that given a Z2 symmetry, there's many quantum systems with the same Z2 symmetry. And similarly, given Z2 topological order in one higher dimension, there's many possible boundaries. The claim is that the quantum system with Z2 symmetry and the boundary of Z2 topological order have a one-to-one correspondence, and so that their physical property just became identical. For example, all the correlation of a local symmetric operator is identical. So therefore, we can using boundary of a topological order to feasibly simulate symmetry, a quantum system with a symmetry. So that is what we claim, that the topological order in one higher dimension, the symmetry are related. So it is in this sense they are related. And so then we see that the boundary of a topological order became very important. So mathematically, we know that the boundary of a topological order and the condenser algebra somehow is closely related. So we can, topological order actually is a Brady diffusion category with non-degenerate. There's condenser algebra in it. And so given condenser algebra, we can construct a boundary. And this condenser algebra physically, basically, it's just a collection of anions. And all those anions have a bosonic statistics, have a trivial mutual statistics between them, and they are closed under fusion. So that's some kind of a very simple-minded description of condenser algebra. Then for each set of condenser algebra, you can obtain a boundary. And so that is that's why the condenser algebra now play a very important role. Okay. And then for this, for our example, like we have a Z2 topological or Tor code in 2+1 dimension. And what kind of condenser algebra it has? So the Tor code have this extension E, M, F, and 1. 1 is a trivial extension. And one of condenser algebra is this 1 plus M. So this M extension and plus this trivial extension, that's one of condenser algebra. And another condenser algebra is 1 plus E. These two condenser algebra are maximum in a sense that they are not a sub-algebra of some other condenser algebra. It turns out that for this maximal condenser algebra, which is also called the Lagrangian, you get a gap boundary. If you're condensing those anions to the boundary, you get the gapped boundary. And these two gapped boundaries happen to correspond to these Z2 symmetric states and Z2 symmetry breaking states. Okay. And so you can see that this condensed algebra and the phase matter with Z2 symmetry have a very close relation. And there is another simple condensed algebra, just a trivial particle. And this is not a maximum. And this non-maximum condensed algebra gave rise to the gapless boundary. And this gapless boundary corresponds to critical point between the Z2 symmetric states and the Z2 symmetry breaking state. There's a phase transition, and the critical point is a gapless. And this gapless critical point happens to be described by this condensed algebra of 1. So from here, you can see that the different condensable algebra in the topological order in one higher dimension correspond to different phase matter with that corresponding symmetry. And this kind of picture works for both gapless states, which described by maximum condensed algebra, and the gapless states, which described by non-maximum condensed algebra. So this kind of a picture we try to present, yeah. And so let's consider a little bit more non-trivial example. Let's consider the 1+1 dimensional system with a Z2A plus Z2B symmetry. So their bulk will be the quantum double of Z2A times Z2B. Or it's a gauge theory with a gauge group Z2A times Z2B. So it's maybe the two copy of a categorical model. So depending on which field, so there's different description of the same thing. And they have this onion of Z2A have this kind of onion, Z2B have this kind of onion, and the bound state between these two. So that's kind of onion we have. And then we can get this all the condensed algebra to this Z2 cross Z2 quantum double. So those are this 6 maximum one or 6 Lagrangian condensed algebra. And the first 4 actually describing the different symmetry breaking pattern of Z2A, Z2B, because each one can be broken or unbroken. So there's 4 choices. And there is one choice which is break Z2 and Z2A, Z2B, but leave some diagonal Z2 unbroken. And the last one corresponds to this kind of another gapless states, which actually correspond to this Z2A plus Z2B SPD states. So this gave example that this condensed algebra kind of classify these symmetry breaking states, SPD states in higher dimensional being SET states. So this is a kind of unified way to understand all the gap phase matter using the categorical symmetry in topological order in one higher dimension plus its own condensable algebra. Okay, and so this so now let's consider a little bit more non-trivial example. And so we consider 1+1 dimensional system with an S3 symmetry. So that's a non-abelian, simply it's a non-abelian group. And the categorical symmetry of the corresponding topological order in one higher dimension corresponds to S3 quantum double. Or in physics, we call this S3 gauge theory. And so in this S3 gauge theory, in 2+1 dimension, there's 8 kind of quasi-particle, plus trivial one plus 7 non-trivial one. And in physics, we say that 2 of onion is actually a representation, irreducible representation for S3, which have a 2 irreducible representation. And then the S3 representation also have a 2, S3 group also have a 2 conjugated class, which correspond to so-called gauge flux in the gauge theory, a flux-like excitation gauge theory. And then there's a bound state between the charge and the flux. So there's a P1, P2, and C1. So this gives us this 7 non-trivial particle plus a trivial particle, and they have this fusion rule described here. Okay. So what is a condensable algebra in this S3 quantum double or S3 gauge theory? And this is a little bit non-trivial, and so there's a way to compute this. Not a complete. I mean, there's a practical way to compute this, and but this practical way sometimes give you some fake results. But for this simple case, it's okay. Yeah, please. Yeah, this is very, very good. So because the condensed algebra, you need to have algebra. And here, this one, I only gave you the vector space. So there are data to describe algebras, which I ignored here. So I just present algebra just given the vector space. And because of the full description condensed algebra is much more complicated. There's a lot more data. And but here just using some simple-minded description. Yeah. And yeah. So indeed, this is a this case. Yeah. So for this S3 condensable, there's 8 condensable algebra, and the first 4 are maximal or Lagrangian. And these 4 Lagrangian condensed algebra happen to correspond to 4 familiar states because this maximum condensed algebra corresponds to gap states. When you have S3 symmetry, what kind of gap state do you have? Well, naturally, according to Landau theory, we have a different pattern of symmetry breaking. Actually, S3 group have four different subgroups, and so this S3, Z2, Z3, and Z1 is the 4 subgroup of S3 group. And it corresponds to the gap state, which with no symmetry breaking have full S3 symmetry. You have some symmetry breaking, you still have a Z2 or Z3 symmetry remaining, or you break all the symmetry, you have trivial group Z1 symmetry at one energy. So it's very natural. We have these 4 states, which correspond to 4 maximum condensable algebra. And but however, there's no more. So that means there's no SPD states. Indeed, from this group cohomology calculation, we find S3 as 1 + 1 dimension indeed have no SPD states. So the only symmetry breaking states gave rise to all the gap states. Okay, so that is this picture. So the 4 corners are these 4 gap states. Okay. Then there's a 4 non-maximal condensable algebra. It's supposed to correspond to gapless states. So what is those gapless states? And that is a key question. So what is those gapless states? So we want to understand those gapless states. And so in 1 + 1 dimension, there's a way to obtain the gapless states using so-called conformal or modular bootstrap or conformal bootstrap. Okay. The idea is that the partition function of a 1 + 1 dimensional system depends on the shape of a space-time. And this tau parameter describes the shape of a space-time, which is taken to be a torus. I have a torus, choose different metric, have different shape, and this tau is describing the shape. Then the partition function as a function of tau have this modular invariance property. And then using this modular invariance property plus some algebraic property I won't describe here, then we can somehow one can determine this partition function more or less completely. I mean, you know, certainly there's many modular invariant partition function, but there's some discrete set. So we have some kind of a classification here. Okay. However, here we have something very similar because we are talking about the topological order. We are talking about the boundary of a topological order, and this boundary can be gapless. And how to describe this boundary gapless states? Again, we're using this idea. We can using the boundary partition function, and it have a modular invariant property. But however, as a boundary partition function, we find that the boundary partition function have many components. It's not a single partition function. We have many of them because we can insert so this is a picture of a 2 + 1 dimensional space-time, and this blue one is a topological order, and we can insert word lines onions in the 2 + 1 dimensional space-time. This word line onion modify the boundary sector, which gave rise to different boundary partition function. So therefore, the component of a boundary partition function is labeled by the onion in the bulk. So then we have this bunch of a partition function, multi-component partition function, and they are modular covariant. So under modular transformation, they are modular covariant given by this ST matrix, which is from repetition of SL2Z group. And this ST matrix happen to be the ST matrix of modular data describing the bulk Bragg diffusion category. Okay, so that's a connection. If you know the modular data for the bulk modular tensor category, then you can obtain is a gapless boundary by looking for the solution of this type, modular covariant partition function. So this represents an algebraic way to obtain the gapless boundary of a bulk topology order. So here is just some result. We just in 1+1 dimension, we have a library of conformal field theory, which give us conformal characters. Then you can use those conformal characters to construct the multi-component partition function, which satisfy this modular covariant property. And so we just do some kind of a search. And for example, we find that this is a modular covariant partition function. That's one of the modular covariant partition function, which describe a gapless states, a gapless boundary. Then you may ask, well, this gapless boundary corresponds to which condensable algebra? It turns out that we can see that there is a trivial conformal character for the trivial primary field, which is chi0 squared. The chi0 squared only appears in the first component of the partition function. These components are labeled by onion types. And because this character only appears in the first component, that means this particular solution corresponds to this kind of condensable algebra 1, just a trivial 1. Okay. So this basically is the answer. The gapless boundary for this condensable algebra 1 correspond to this CFT. We get this partition function. And this solution is not unique. For example, we can have another solution for condensed algebra 1. That's another CFT. But this CFT is constructed by this 7-6 minimum model, which is more unstable, have a higher central charge. And this blue one actually have 2 relevant operators. And the first one is more stable, have only 1 relevant operator. So this gives you some flavor, from this condensed algebra and from some algebraic approach, you can calculate some candidate CFT. And there are some other things. For example, this one, this is yet another solution. So we have some 0. But now you can see there's a chi0 squared appear in both 1 component and A1 component. So this corresponds to condensed algebra 1 plus A. The gapless boundary of this condensed algebra is given by this kind of CFT. So okay, so at the end we get this picture that the maximal condensed algebra gave rise to the gapless states, and the non-maximal condensed algebra give you CFTs, gapless states, and we can identify which CFT are they. Okay. So now we ask a physical question, and so we know that for the gapless states, we can have phase transition from one gapless state to another gapless state. And the critical point of phase transition is given by the gapless states. But which gapless states? So you have to pick, there's many pairs you can have a phase transition. But which gapless states? And it's actually pretty natural. You can see for this S3 state with this condensed algebra and the Z3 state with this condensed algebra, we can see that they have a common subalgebra 1 plus B. So it's very natural to think this 1 plus B describe a gapless states, which is a critical point of phase transition between S3 to Z3. Okay. And also we can see that from S3 to Z1, their common condensed algebra is only 1. Okay. So therefore, this condensed gapless state for condensed algebra 1 should describe a critical point between S3 to Z1 transition. Then we have also from S3 to Z2. From S3 to Z2, the common condensed algebra is 1 plus C. You can see the 1 plus C is a common thing. But here's something interesting. 1 plus C is not a condensed algebra. You know, it's failed some other condition. You know, it's actually, it's question about the condensed algebra is not just a space, there's algebraic structure there. That algebraic structure does not work in this case. So here we have a puzzle. Then we cannot have 1 plus C. So we have to go to 1. So then we conclude that the transition from S3 to Z2 is also given by this condensed algebra 1. So that's a lead to this statement. The phase transition from S3 to Z1 critical point, and the phase transition from S3. Oh, sorry, this is the bug. This should be S3. One is S3 to Z2, another S3 to Z1. S3 to Z1. These two phase transitions should be described by identical critical point. It's just a condensed algebra of 1. And this is very strange because physics, we think for different symmetry breaking pattern, we should have a different critical theory. But here we conclude that these two different symmetry breaking patterns have same critical theory. So in some sense, I don't want to believe this. So one way out is that maybe one of phase transition can never be a continuous phase transition. And but however, we already know that S3 to Z2 can be a stable transition. So let's let us to guess. Maybe S3 to Z1 phase transition, which is allowed phase transition by Landau symmetry breaking theory. We probably do not have a continuous phase transition between S3 to Z1. Yeah, so this may be the one of a new result from this categorical symmetry analysis. Either these two transitions described by same critical point, or maybe S3 to Z1, this transition just do not exist as a stable continuous transition. So it's one of the results. Okay, and so actually we did some numerical calculation. We tried to looking for the direct transition from S3 to Z1. So actually there's several phase diagrams. So we need to find the direct transition from S3 to Z1, but that transition is first order. And we're still looking for the second order phase transition, direct transition from S3 to Z1. We haven't found it yet. But however, we do find someone a multi-critical point. There's a direct transition from S3 to Z1 as a continuous transition, but it's a multi-critical point. And at this point, also have a direct continuous transition from Z3 to Z2. That's a Landau forbidden transition. And this multi-critical point we believe to be described by this by this unstable CFT, which is two relevant operator. So this Wiener model 7-6 Wiener model may describe this multi-critical point at this point. And so maybe there's another result. Okay, and so we also find that S3 symmetry can have anomalies. The anomaly in one dimensional anomalous S3 symmetry are classified by this group homology, which is Z6. So this I'm just label different type of anomaly. Then you find that if M equals 3, the condensed algebra will be different. And so there's a 2 gapless phase and 4 gapless phase, and those are corresponding CFT. The last one, I think, is some kind of orbifold, and but we could not really completely pin down, so we're still working on that. And interesting that for the second type anomaly, we somehow figure out all the gapless states. The last one is pretty interesting. This condensable algebra 1 gave rise to a chiral CFT. The right mover is a SO9 level 2, and the left mover is a E8 level 1. And this chiral CFT corresponds to boundary of this S3 the second type anomaly. And certainly there's an issue, how to describe the phase transition and critical point and etc. And so So this is the summary, and so we see that I'm hoping to demonstrate that by studying emergent symmetry in the gapless states, and by realizing that emergent symmetry can be very, very rich, then maybe we can use an emergent symmetry to largely almost characterize these gapless states. So every gapless state have emergent symmetry, and then by studying emergent symmetry, we probably can get a general understanding of gapless states. Yeah, thank you very much.
So you said,
could people please, we were asked, would you identify yourself when you're asking a question?
hi, yeah, this is Sean Cui. You said for the anyons in the condensable algebra, they are closed under fusion.
Yeah.
But for example, in your S3 case, 1 plus A2, is it closed under fusion? A2, yeah, 1 plus A2. A2, is A2 the two-dimensional representation of?
Yeah, but this yeah, but I think yes, but they have a different I think they have a different the fusion rule is modified, I think, in this case.
So it's not the regular fusion of S3 representation, or double S3 representation.
Yeah, I should print that out. Yeah, I think so. Yeah, it's a different model category.
Okay.
Yeah,
okay.
and but I should print out the fusion to examine that. It's different model category. It's it may the fusion rule may or may not be the same, but I think maybe here it can be different. Yeah.
Okay.
Yeah.
Okay. Good. Thanks.
So Iris Kong here. Thanks for the great talk. I'm used to considering condensable algebras more in the context of like gap boundaries and like kind of domain walls between phases, in which case like these are maximal algebras, like the Lagrangian ones that you considered are like the gap boundaries, right? But then like the like condensable algebra with non-maximal dimension is like kind of domain wall between like two different topologically ordered states.
Yeah, exactly. And so there's another way to look at this. That is the maximum condensed algebra is a boundary between topological order and the trivial states.
Right.
The non-maximum condensed algebra either correspond to gapless boundary or correspond to domain wall between one topological order to another smaller topological order. And this smaller topological order can be viewed as an unbroken categorical symmetry.
Okay.
And then the one condensed domain wall of this smaller topological order correspond to original gapless boundary. Because in a smaller topological order, you already have anion condensation. Then you consider one condensed boundary, you do not have additional condensation. So one condensed boundary of a smaller topological order describing gapless states. And so from this point of view, we can say that every gapless state can be viewed as a one condensed boundary of some smaller topological order. So that's another way to classify gapless states. From the topological order to unbroken categorical symmetry and to the one condensed boundary or canonical boundary of this smaller topological order. So that's another way to view this picture. Yeah.
Yeah.
This is Christopher Moudry. Can you deal with anti-unitary symmetries?
What?
Can you deal with anti-unitary symmetries?
No, at the moment, no. Maybe yes. You know, so far I only consider internal symmetry. I don't have a space-time symmetry. So I don't know how to handle space-time symmetry. So that's related to this anti-unitary symmetry, which is time reversal symmetry. On the other hand, so this is a really very good question. That's whether there is a category theory not based on the complex number C, but based on real number R. And that formulation apparently to be more suitable for the time reversal symmetry. So I'm kind of thinking this category theory based on real number R is for time-reversal symmetry, and then the similar story may work in that setting. Yeah, that's one way to understand the time-reversal symmetry. Yeah.
Please say your name slowly so that we can understand.
Hi, this is Nat Tandiwasadakan. I wanted to ask that, so you identify a non-Lagrangian algebra with a, is it true that the non-Lagrangian algebra doesn't correspond uniquely to a certain CFT? So it's just the most lowest like stable one? And if so, how can we study other CFTs that might have the same non-Lagrangian algebra?
Okay, I didn't quite get it, but let me think about. Yeah, there's one thing, there's one caveat that kind of hide. I try to say for the given condensed algebra you get a CFT, which is a lie actually. We can see that for the given condensed algebra with one condensed algebra we get a two CFT. Yeah, but here because in physics we mainly interested in the CFT with a most stable one. And so therefore, for the given condensed algebra, you may get a few stable one. And so in this sense, condensed algebra and the gapless states have some good correspondence. So by studying condensed algebra, we have some kind of larger understand the gapless states, because we're looking for the most stable gapless states. And then you may say, when you have a gapless state which is not most stable, have some additional gapless excitation. And I'm thinking, actually this is, I don't know, but I'm thinking maybe in this case, you have additional emergent symmetry. Your previous emergent symmetry is too small. You should enlarge your emergent symmetry. And then maybe this more unstable CFT became a stable one for this enlarged symmetry. So in this way, maybe there's a more one-to-one correspondence. But this is really still open, and we still try to push in this direction to see whether we can get some good results in this direction.
So like toric code, I can have Ising model, but say if I consider instead tri-critical Ising model, does that correspond to some different bulk?
Yeah, that's a good question. But the example I know that is for the Ising model can be viewed as a boundary of a toric code, the ordinary Ising critical point. Can also be viewed as a boundary for double Ising model, or so double Samyang. So the double Samyang is representing a bigger categorical symmetry. So I would say this the Ising critical point have a larger emergent symmetry, which is double Samyang, not toric code. So in this larger emergent symmetry, the EM exchange duality symmetry was included. In the ordinary, if you view Ising model as a boundary of toric code, you did not include the EM exchange symmetry, which is a symmetry at the critical point, but not symmetry away from the critical point. Yeah, so that's it. Maybe related.
No question. Just quickly, Zhenhan Wang. So, for example, both are doubles. The CFT you get seem like both are full CFTs. Suppose you get a chiral, model tensor category. Do you get a boundary to be a chiral CFT?
Yes, and so this is you can see the example. Let me try this. The example I gave have a so-called gapped boundaries. So in a sense, they are kind of it's a trivial center or something. And we know that the topological order have a chiral topological order, which is not a trivial center for any fusion category. So what is that? And I don't know. Yeah, but so that means we probably need to generalize the notion of symmetry even more. You can see the previous symmetry we described, although it's a very long list, but they all have a common property. They allow gapped states. But there may be even symmetry which do not allow any gapped states. And that symmetry corresponds to chiral topological order in the bulk. And so maybe you should also view that as symmetry. And certainly that one also may not have a Lagrangian condensed algebra, but may have many non-Lagrangian one, and that may correspond different gap states of that. Yeah.
is the Fibonacci.
Yeah. Oh, that's true. This
That's
the double Fibonacci in the bulk. The boundary should be this golden chain. Yeah, you studied. And actually the symmetry of that golden chain is not I'm not sure, maybe not in my list. You even have a very big list, that's still incomplete. But the topology order in one higher dimension may give you maybe more systematic description. Yeah.